Energy efficiency of buildings is a priority. In the European Union, three-quarters of all buildings are not efficient. Buildings consume 40% of total energy use and emit more than a third of greenhouse gas emissions. There are alternatives to reduce their energy consumption and, consequently, their environmental impact. Architectural design can achieve this by connecting the building with its context, selecting appropriate materials, incorporating passive systems or, failing that, energy efficient equipment, and utilizing renewable energy sources. The architect's mission is to achieve comfortable spaces with minimal energy consumption, low environmental impact, and high cost effectiveness. These decisions regularly result in a positive performance, although their accuracy is unknown. Building simulation software performs energy, thermal, lighting, and environmental analysis, among others. Architectural design assistance programs no longer simply assist with drawing or modeling the building. They can now verify the performance of the design. However, the design improvement process is often inefficient. The proposal is modified repeatedly until the established objectives are met. Architectural design involves a large number of variables, elements that are linked to others. Considering all these variables in a limited time frame is a virtually impossible task for an architect. However, new technologies have opened up new horizons in disciplines such as architecture. Research is already using artificial intelligence to generate more precise designs based on sustainability criteria. This technological advancement makes achieving the environmental goals set at the government level more tangible. According to European Directive 2024-1275, starting in 2030, all buildings must be zero-emission buildings, that is, buildings that use little energy to operate, with low greenhouse gas emissions and very low CO2 emissions. In this context, the project Innovative Methodologies for the Design of Zero-Emission and Cost-Effective Buildings, enhanced by Artificial Intelligence, (SEBAI), emerged. This Horizon project involves 18 partners from 7 European countries. SEBAI seeks to create a tool that optimizes buildings design through an evolutionary algorithm. To assess the quality of the solutions, the tool will evaluate multiple criteria through different analyses and simulations: energy performance, thermal comfort and air quality, carbon footprint, daylight comfort, cost, and compliance with local and national regulations. The tool is based on 5 key inputs: material catalog, building configuration catalog, regulations and standards, design restrictions, user preferences, environmental and location data, preliminary building design. Using these inputs, the tool produces design proposals, evaluates them using the aforementioned analysis, and iteratively refines them using an optimization algorithm. Upon completion of the optimization process, the tool provides the user with solutions that met regulation, user preferences, and given constraints, achieve excellent performance across key evaluation criteria. Finally, the expert user can review the generated solutions and select the most appropriate option based on the specific needs of the construction project. The objective of this paper is to explain the criteria considered for catalog creation, definition of functions, required properties, information sources, material characterization, reference databases, and considerations for updating. The paper focuses on the performance analysis, energy and thermal, that will be carried out using the simulation tool. The catalog will serve a dual purpose. It will be used for the survey project simulation and optimization processes, and it will also serve as an open source of information for those interested or inquiring about it. The properties required by the simulation tool Energy Plus will be integrated. Roughness, thickness, density, thermal conductivity, specific heat, emissivity, water vapor diffusion resistance factor, and solar and visible absorbances. The information available on products is not always consistent, and some properties required for analysis are frequently missing. Regarding thermal and energy analysis, physical, hydrothermal, and optical property measurement will be performed to supplement the information. Thermal conductivity measurements shall be performed using the guarded hot plate method and the hot wire method in accordance with the corresponding standard. The water vapor diffusion resistance factor will also be measured following the procedure indicated in the corresponding standard. Beyond glazing, the optical properties of opaque materials have been shown to influence a building's thermal and energy performance. However, these properties are generally not considered in product information. Therefore, the solar and visible reflectance of opaque materials is planned to be measured using spectrometers to calculate solar and visible absorbance coefficients according to the corresponding standards. In addition, emissivity is also planned to be measured using an emissometer. The SURVEY project aims to develop a methodology that uses AI to encourage the architectural design process of zero-emission buildings. The methodology includes different analyses: thermal, energy, regulatory, environmental, and cost effectiveness. To carry out the analysis, a catalog is required that provides the properties of commercial construction materials. This paper focuses on showing the criteria that were taken on create this material catalog, specifically on the properties necessary for the thermal and energy analysis. The Survey Materials Catalog aims to fill a gap in current information, providing a data source that, in addition to its use for the project, is of a public nature, available for consultation by anyone who requires it.